Hello everyone, welcome to MLAS100, where we are going to jump into an update, specifically a 2022 update of Learning Activity 5, Limitations and Statistical Biases. And we're not gonna jump through all of it, but all of the different limitations. And there's no update to the statistical biases. We'll stick to a few updates as it relates to limitations, so this won't be a super long lecture. But there's so much that's happened since 2021, the last time I recorded this. I wanted to lay down a new video so that you got the latest between 2021 and 2022. So let's go ahead and jump into the first. Let's go ahead and jump into rather the overview of what we're going to cover. And all right, here we go. So first up, we'll talk about limitation 1. We'll circle back on Dataism and a little bit more nuanced in terms of the way that, or rather new information as it relates to limitation number 1. Limitation number 2, I want to talk a little bit more about deterministic versus stochastic, and kind of go into, that's actually will be 2 parts to that. We'll go through, and I've got some Python code that should help to explain the differences between determinism and stochasticism. And we actually will be covering a lot more of deterministic machines and stochastic machines and semi-stochastic and semi-deterministic as it relates to Turing machines, but we'll do that in MLAS100. And that's something that we'll cover in more detail, but I did want to give a little bit more of an introductory build out as it relates to that topic. We'll also talk a little bit about the maths involved. I know some people are like, well, what kind of maths really are involved in terms of AI and machine learning? We're primarily developing machine learning engineers in this program, so while we do cover a fair bit of a little bit of math within the program itself, we're not trying to make statisticians or mathematicians in the program. So as far as it relates to this, it'll stay high level. Limitation number 3 is just about the data intensity as it relates to different situations. I did want to expand on it. You know, I wanted to kind of, in the original video, I wanted to keep things simple, but I felt like an update was warranted. Still keeping it simple for now, but I want to talk about updates as it relates to the evolvement of machine learning, particularly in the last few years, but how there's been a shift towards, or rather an architectural view of machine learning frameworks in terms of more data intense versus less data intense. There's been kind of this bifurcation in the area, in machine learning specifically, as it relates to that. So anyway, that's about all for the high level agenda. Let's go ahead and go into limitation number 1, which is Dataism and trusting data. So I wanted to talk a little bit more about the difference between trust as it relates to data, but then expand on that conversation as it relates to trust versus artificial intelligence. So you do remember from the lecture that I talked about, there's this funny situation where the driver actually was following the GPS and drove straight into a lake. And trusted the GPS so much so that of course they got their car underwater. But we have other areas of trust that are pretty interesting as it relates to data. So we trust, of course, our GPS for the most part. We trust emergency alert systems. We trust healthcare for the most part. Our healthcare system, and there's other areas that for the most part, humans, we trust I mean, there's always exceptions. There's always things that pop up. There's always outliers. Humans are known for behaving in ways that are not always consistent, right? Even though that you'll create a set of data points in terms of how you act, and we can always act outside of the way that we've been raised, right? So that happens in machines as well, right? That happens in data. That happens. There's always outliers, and that's what's going to come up where I want to talk about in a little bit more detail between deterministic versus stochastic. But it's interesting because while we trust data, there's this kind of this gradient in terms of I do trust. I think most of us trust our GPS, you know. And if you look at this gradient triangle on the left here, you do have this more trust. But the trust starts to whittle down as we start to get into more critical functions. So, and that's something that we still haven't figured out how we're evolving through that process. So as an example, I throw up here, if we were to replace the U.S. Supreme Court judges with an AI judge, would we as a country feel comfortable with that? And even if we made it like down to a local level, let's say we replaced our local magistrates with an AI judge, right, versus an elected official, you would probably have some people that would be worked up about that, right? And there would probably be a certain part of the population that would be, hey, I'm all on board with that, right? Take the human morality, take the human judgments, take all that out the window, and then let an AI do the judging. There's all kinds of other things like that. There was a recent study that I had come across where the Air Force was actually doing trust as it relates to artificial intelligence, pilots trusting an AI co-pilot. And it turns out a lot of the pilots didn't trust the AI, but if the AI was replaced with a human and the co-pilot was taking directions from an AI, the pilot in command actually felt more comfortable. So there's situations where we still have a ways to go, even though for the most part, especially when it comes to non-contentious type of scenarios, they might be complicated, but non-contentious, for example, like autopilot with an airplane. I think a lot of people are actually getting around to starting to trust that, and actually easily within the next 10 years, there's going to be more and more trust as it relates to more and more critical functions. So with that's just the extra thing I wanted to talk about when it comes to trusting not just data but artificial intelligence, and that's an area to be thinking about as you go along through the curriculum. Okay, next up, let's talk about determinism versus stochasticism, or stochastic versus deterministic. This is a little mini lab, optional if you want. This is written in Python. Code on the right is something that I put together specifically for this slot, for this lesson plan. So I cranked out some of this code here quickly just to kind of give an idea of the difference between in programming, right, in a programmatic, probabilistic programmatic sense. I wanted to show the differences between what stochastic versus deterministic look like. I talked about it high level in 2021, but for the update here, I want to give it a little bit more of a deeper treatment, as it were. So deterministic functions is the blue line. And when you look at what determinism means, it's the easiest way to explain it, and the way that I felt was a simple way to explain it is a sine wave. So if I create a sine wave that follows a curve, and it's a curve based on an equation, and that's probably the easiest way to describe determinism. It's an equation. And it's a deterministic equation where there is no probabilistic functionality to it. In other words, there can a deterministic equation or deterministic learning model can never deviate from its path plan. It always has to stay on the blue line. Now, a stochastic model has the ability to deviate from its path plan. So it uses randomness to help deviate from the line. So if you actually look at this, the cyan data points that are on here are a noisy randomized sine wave. And so what we did was I added a random function into I introduced a randomizer into the sine wave function so that it deviated from the path, but it still approximates the path and fits it pretty well. So, and we'll talk about how this actually works down the road, where we talk about model, or rather, the fitness, or the fit of a model to a given line. And this is a good way to kind of introduce that topic, but we'll talk about fitness metrics and those type of things as we start to get through and get further on into your studies within the program. But for now, this is a good way to do it. You can write this up and you can play around with the variables here. So you can see what happens. As an example, you can actually take the NumPy, the Python NumPy library, where it says np.random.normal, and there's a scale equal to 0.18. You can actually play with that scale a little bit. That's actually the boundary of how far it goes. So this is, while it's stochastic, we'd call this a physics-informed stochastic model. So it's technically still has some slight determinism in it, but that's something that for the purposes of for educative purposes, this is plenty to kind of illustrate the point between stochastic, which uses random or probabilistic functions to help a system deviate from its intended planning path, versus a deterministic a system that can never deviate from a cognition path or a planning path. So this is this piece of it. Feel free to code this out. Again, it's optional. You don't have to do this. If my explanation here is enough, then you're good to go. Okay. So let's follow this up with deterministic problems, part 2. I know this comes up, deterministic, stochastic, semi-stochastic. A lot of AI frameworks. They're actually more modern frameworks, although you'll still see it quite a bit where researchers are focused on a specific algorithm and trying to solve the world's problems with a specific algorithm. It's just not a really, it's not a realistic route. Most machine or cognitive processing engines, i.e. the human brain, which is a biological computer unto itself, it uses multiple algorithms, multiple models. So it's not something where one algorithm rules it all. Most often, modern AI frameworks use what's called ensemble learning methods, which means it uses multiple machine learning methods. So in this case, that also has a direct impact in terms of what maths are used. So you'll see here where linear algebra is quite a bit. You get quite a bit of that. A little bit of multivariate calculus. There's also probability theory and statistics. So you've got about let's see, between probability theory and statistics, multivariate calculus, and linear algebra, you've probably covered a large majority. So I mean, that's probably a majority of it. So that's why you see, while you'll have in your math course outlay a healthy dose of your calculus with linear algebra kind of combined there, so you're covering that, but then you've got quite a bit of statistics as it relates to that as well. So there's some other pieces where there's algorithms and complexity. That's actually a machine learning class that everyone should be coming across to, which is data structures as it relates to algorithms. But within that, we talk about time complexity, and then there's this other piece of it where there's just little pieces that take inspiration from other mathematical models. Whether that comes from quantum mechanics, discrete mathematics, differential equations, things like that. There's definitely areas that influence the rest of the machine learning discipline. Again, we're not trying to create mathematicians. We just want to make sure you got a healthy dose of that. So you definitely have a bit of math to run through. But other than that, this should give you a good feel for the type of mathematics involved as it relates to AI and ML, but also that AI and ML applications, they follow a gradient, right? And if we've got an ensemble method, that means there's parts that are deterministic and parts that are stochastic and parts that are semi-stochastic. And honestly, and we will get into this more in MLAS100, where we talk about how this overlays onto machine architectures. And it's very important to kind of have a holistic view before we get into kind of a macro level view, before we zoom in on the hard stuff, which is the probabilistic programming and unsupervised, supervised reinforcement learning in our AI studios. Okay. So on to our last one, part one, is another discussion on an update, rather, in terms of data requirements. So limitation number 3, as it relates to data, I mentioned in the agenda that there's really 2 parts to this. There's areas where there's 2 big, large schools of thought. One is more data, and another one is less data. So, and not one's not wrong, one's not better than the other. They're trying to solve 2 different areas in 2 different ways. So, part 1, this is, this is more intensive. So data, these are areas where they call it a theory of scaling. And a theory of scaling, it postulates that as I make my models bigger with more data and more connectivity, that eventually I'll reach a point of what's called singularity, which means that that's the point at which we've achieved the machine sentience. In other words, a machine becomes self-aware. And that's the theory of scaling, is that you throw more data at it. Now, there's a lot of progress in this. There's large language models, LLMs. There's open knowledge graphs, which is just another form of large language models. They are kind of one and the same to a certain extent. On the left is a open knowledge graph. And then there's a GPT, generative pre-trained transformer. And there's actually a GPT-3 out if you want to go check it out. OpenAI is a very good, it's free, and you can go get an account and interact with GPT-3. These are frameworks that require a massive amount of data. I mean, we're talking a lot of data. And if you've interacted with GPT-3 for any period of time, you'll find it's pretty interesting what the kind of conversations you can have with it. I probably pop it up once a week to just kind of get questions to answers. That actually is a useful aid for me in terms of trying to track down information quickly. And GPT-3 is pretty cool and provides and it's also good for me from a research perspective to see its capabilities. Soon after GPT-3, probably within the next year or two, 2023, maybe probably more like 2024, but GPT-4 is going to get released, and it's supposed to approximate the neuronal connectivity of the human mind. So it'll be interesting to see what ends up happening with GPT-4 and how soon they'll release that. On the other side of the spectrum is the less intensive part. So this is the last side I want to talk through in terms of an update, because it's an area of interest in terms of what we do here on campus. But there's, on the other side of it, is making data less intensive, or a less intensive data requirement is another part of the limitation conversation we're having. So one is, of course, more data. The other one is less data. And again, they both operate in different ways. So the reason why I would want to have less data is computational. It takes more power to run compute. So to do a calculation on a computer, it takes power. And if you're running, like, say, for example, an aerospace application or a space-based application, power is very important and you want to be able to run machine learning activities in autonomous systems, not an automatic control system. That's automation. That's procedural, deterministic, industrial machines. When we're talking about stochastic or semi-stochastic machines, then or I would say deterministic machines that are stochastic enabled. That's another way to think about it. It just depends on the architecture, but you have you want to have less data for certain tasks because it draws a lot of power to run massive, large language models. When you open knowledge graphs are computer intensive, but there's interesting areas where we're talking about increasing our ability to use less data while doing the same thing. So physics informed neural networks is one. Neuromorphic learning methods, which is kind of more of it's an emergent area it's been around. The concepts of neuromorphic learning have been around for a while, but the ability to execute on it from a hardware perspective, it's kind of like quantum computing. It's actually more robust in terms of its ability to, from a hardware perspective. The accessibility of quantum hardware is very far and few between, whereas neuromorphic learning methods, as well as the associated hardware for that, is more accessible. That's kind of where I'm going. Machine learning micromodels, there's a lot of interest in this as well, as it relates to taking and shrinking down, not just from a physics informed perspective, but taking micromodels and shrinking them down to where they run on less, to where I can run them on Raspberry Pis, where I could run a machine learning model even on an Arduino, or even maybe something smaller like a floating point gate array, which is what you see here in the picture, an FPGA. That stands for floating point gate array. And we've got some expertise around that here on campus, around FPGAs and SBCs and Jetson Nanos and Raspberry Pis and Arduinos, and so we actually are going to start off with a microbit controller, an MLAS100, for part of your cybernetic project kit. Your CPK that you're going to order for that is going to have a microbit controller that you'll learn to block code, and then you'll learn to impart your code. It's available in JavaScript as well as Python, but we'll start off in block code for a majority of the class, and we'll touch on Python as optional lab exercises in MLAS200. But for sure, we'll be exploring a lot of the autonomous systems components of the work through creating through our cybernetic project kit in MLAS200. So you'll actually start to see where we imbue hardware with code and get experience and practice with that. Okay, I think that's all I have for this particular update. I appreciate it, and I look forward to seeing everyone later this week in our optional sync and or online. We'll talk to you later.